Okay, this is a video on the day 1 on confidence intervals. So what we're going to do today is determine the point estimate, margin of error, and standard error from a confidence interval. Feel free to pause this video at any time to catch up on the notes or the vocabulary. So inferential statistics, the goal is to make inferences or draw conclusions about population parameters from sample statistics. Usually cheaper and easier, so it's very hard to find the average for an entire population, but we can take a sample of that population, find the average or some sort of relative frequency, and make an assumption or an inference about the entire population. And what we're going to use from that sample is called a point estimate. It's a single value estimate for a population parameter. The most unbiased point estimate of the population parameter is the sample statistics. So for instance, if I'm trying to predict mu, the average for a population, I would use X bar, the average for a sample. Okay, and then a confidence interval is an interval or a range of values used to estimate a population parameter. Point estimate is going to be the center, and the margin of error is subtracted from and added to it. The margin of error accounts for the width of the interval. So it could be written in two ways. You can write it as the point estimate first, plus or minus the margin of error, or it can be a range of values with the population parameter in the middle. For example, it's going to look like this. So you have your point estimate plus or minus your margin of error. This is your critical value of Z. And this is what we call our standard error. So if I have to add or subtract that margin of error is actually composed of the critical value of Z times standard error. And there is a formula for standard error that we will use. It's going to be standard deviation S over square root N. Okay, and here's an example. So if I wanted to find, say, the average price of all, or the average amount that all babysitters charge in the New Orleans area, well, that would be near impossible for me to find, but I can find a sample of, say, 50 babysitters, find the average from them to make an assumption for the entire population. So if the average for the sample is 15.48. I would put that as my point estimate, plus or minus, here's my critical value for Z, and standard error. Once you multiply to get your margin of error here, to get $1.25, you add and subtract it. You would subtract to get the lower bound right here. And then you would take 15.48 plus 1.25, that margin of error, to get the upper bound for your range. And then we put mu in the middle, again, because we're trying to estimate mu, our population parameter, using X bar. And this is kind of a picture of what this looks like. A 90% confidence interval, so I'm 90% confident that the average for all babysitters is between 14.23 and 16.73. So again, we would say that we are 90% confident the population mean is within the interval. Not that there's a 90% chance that the population mean is within the interval. I know that sounds pretty similar, but it is different statistically speaking. Okay, then confidence level. So there's different types of confidence intervals we can make dependent on our confidence level. So that's how confident you are that your confidence level contains the population parameter. usually written as a percent. Alpha is your chance of error, and it's written as a proportion. Critical value of Z used to separate the probable from improbable sample statistic values. And this I would highly suggest you need to memorize. So this is the most common confidence levels, 90%, 95%, 99%. Your alpha levels are the second column, and your critical value for Z is the last column. Alpha is usually given as a proportion again. So if I'm 90% confident, that would mean that there's a 10% chance for error, and 10% as a proportion would be 0.01. Again, if I'm 95% confident, well, there's a 5% chance of error, and 5% as a proportion would be 0.05, so on and so on. Okay, now for some class examples, or some examples we did as a class. What is the best point estimate for the population mean? Given N is 1410 customers, the mode is 3 miles per hour, median is 3.5 miles per hour, X bar, the average is 3.01 miles per hour, and the standard deviation is 0.21. Well, if I'm trying to estimate population mean, the best point estimate would be the sample mean. So it would be 3.01 miles per hour. For number 2, determine the point estimate and the population, for the population and the margin of error. Okay, well here it's in the form of point estimate plus or minus the margin of error. So here, point estimate, when it's percent, we're going to write that as a proportion. So 0.52, oops. Margin of error is what's being added or subtracted, so that would be actually we can write it as a percent, sorry. 4.5, okay. Okay, here, determine the point estimate for the population and the margin of error. Okay, so when it's given a range, to find basically the middle, sorry, I had to grab my calculator. What we're gonna do is add those values and divide by 2. Because again, I'm gonna go back to this picture. If here is your lower bound value and your upper bound value, well, to find the middle, you're going to add those 2 values together and divide by 2. So 7.1 plus 9.8 divided by 2. Okay, so point estimate, 8.45 homicides. Okay, and then for your margin of error, your margin of error accounts for the width of your interval. So to see how far wide this is, take the upper bound, 9.8 minus 8.45. Okay, so the margin of error is 1.35 homicides. Okay, here we have a confidence interval, and we are going to find all of those things it's asking for: the point estimate, excuse me, standard error, critical value of Z, and confidence level. So when it's in this range, in this format, it's the point estimate plus or minus critical value of Z times the standard error, 0.01126. Okay, so then point estimate it's not a proportion, it's not a percent, so we used X bar here, so 51.2 days. Standard error would be the last number, oh sorry, right here, so 0.1126 J's. Critical value of Z, 1.96. That's measured in standard deviation, so you don't put a unit. That's very similar to your, basically a Z-score. Critical value of Z. Okay, now that we have the Z-score, sorry, the critical value of Z is 1.96, you can use this table. Since the critical value was 1.96, my confidence level is 95%. Okay, last is the sample size. Okay, so the only formula we have for sample size is right here. So I'm going to plug in 0.1126, 3.56 over square root n. If I rearrange this formula, square root n equals 3.56 divided by 0.1126. Then I would just square that value to solve for n. And I got 999.59. And because that's a sample size, that's going to have to be a whole number. So I would round that to 1,000 cases. Okay, given n is 150 and the 90% confidence interval, find the point estimate, margin of error, and critical value of Z. Okay, so point estimate, again, when it's in this range, you're going to add those together and divide by 2. So 99.8266 plus divided by 2. At 100.2, so point estimate is 100.2 degrees Fahrenheit. Margin of error, again, accounts for the width of your interval. So to see how far wide this is, take the upper bound, 100.5734, minus what would be in the middle, X bar. And I got 0.3734 degrees Fahrenheit. Okay, critical value of Z. They gave you the confidence level, so I'm going to refer back to my chart with a 90% confidence level. My critical value for Z is 1.645. Not that. That's 95. Sorry, 645. Standard error. Okay, so you can find standard error here. Since we have the margin of error, we're going to use the fact that the margin of error is the critical value of Z times standard error. So 0.3734, 1.645, and to solve for standard error, I would divide by 1.645. I do say on the class examples to round to the 10,000th, so let's just say 7 here. Okay, last standard deviation, well, that's in this formula. And let's see, n was 150, so I'm going to multiply 0.227 times the square root of 150. There we go, and that's everything. Okay, last thing we're going to do here. Okay, for this, you're going to need your normal distribution table, your z-score table. Let me get one out. Let's see. Okay. So here, let's start with B. So here, if I'm 75% confident, that means that there's a 25% chance of error. So my alpha level as a proportion would be 0.25. Now to find your critical value of Z, what you're going to do is take that alpha level and divide into 2. Okay, why do you have to divide into 2? Let me bring you back to this picture real quick. Okay, so if I'm 90% confident that my population parameter is between those two values, well, that means that there's a 10% chance of error. And that 10% chance of error comes from 5% right here, 5% right here. So that's why you have to take your alpha level and divide into 2 for both sides of this interval. So once I divide by 2, I got 0.125. Okay, now I'm looking at my table. I'm looking for the proportion closest to 0.125. Okay, and I found 0.1251. That critical value, or that z-score, is negative 1.15. Okay, but for your critical value of Z, you're going to take the absolute value. Since it's the critical value of Z, we take the absolute value, and because we add and subtract this number anyway, we're going to take the absolute value. There we go. Okay, so working kind of backwards, if alpha level is 0.02, well, that adds a percent 2%. So if there's a 2% chance of error, that means I can be 98% confident. Okay, now I'm going to divide my alpha level by 2 to get 0.01. Okay, now I'm back at my table. I'm looking for the decimal closest to 0.01. Let's see, and I found 0.0099. That's going to be the closest to it. Okay, that's z-score, negative 2.33, but let me take the absolute value to get 2.33. All right, and that is it for the first day of notes.